I'm still 2 weeks or so away from finishing the assembly of the Hickman Action in the full piano. So knowing myself, that probably gives around a month until I'm done. So for now, instead, let's cover the control board electronics that I put together. And give me a moment to move me out of the way and get the computer screen up to work as a nice background. I'm trying out something new with this Streamer Lake arrangement, so hopefully this looks good. Yeah, anyhow. So with the experience I have from designing these sensor boards, it only took me a couple of weeks to sketch out these schematics and lay out the board design. Once again, I'm using EasyEDA and ordering through JLC PCB. This time around, I've definitely started to notice the limitations of EasyEDA, at least the standard version. If I have to work on another PCB sometime in the future, I'll probably switch out to the Pro, fortunately still free version. Gonna still stick to EasyEDA and its ecosystem though. The way it's got all the parts, pricing, and footprints already incorporated into the software makes it quite easy to go from finished schematic to laying out the board and then actually doing the ordering without having to do footprint design and comparison and making sure everything is all good. That's all kind of done for you, so rather nice. And with that unsponsored blurb out of the way, let's get on to the design. So here we are in Fusion 360 with the full design of the piano that I've been working on. Let me just hide everything except for the electronics, the custom PCBs more to the point. So in the piano, the control board will sit right here to the left of the keybed. The chain of 11 sensor boards continue along the back and connect to it with the two connectors right there. And all the rest of the components and all of the various connections are at the front. So this means I can just order the manufacturing with one-sided, so it's a lot easier to work around. Originally planned on having this board be around half of its size, but as the scope of included features increased, the board size grew with them until it got to just about the largest size I could comfortably fit in here. I could have maybe gotten a bit more down below here, but then the board wouldn't have been a square shape and it would, been a bit more complicated to get manufactured and all the rest of it. So, you know what, this is good. With a backplate containing all the extra connectors, which I will show in just a moment. So that's the left panel, the left inner components with the computer and everything else. And finally, the back panel for the connections. I've kind of rerouted them a tiny bit. But yeah, isn't a lot of space left along the inside, especially with the connectors right here being so close to the board. So I had to be very mindful of the part selection, as my first pick of the electrolytic capacitors and connectors were much too large, such as this one right here being so close to the hole for the USB connectors. Kind of a good thing too, considering that in my search for smaller electrolytics, I stumbled across the polymer aluminum capacitors, which are better in every way, barring price. Anyway, with the rest of the internals, as I mentioned before, the spacing is getting quite a bit cramped. Most of it is the power supplies and all the rest of it around here. If I were to redo this, I might look into getting a kind of, all-in-one power solution so that, it provides both the 5 volts, the 3 volts for the sensor boards, the 12 volts for the computer, and the 12 volts for the ADC unit, but realistically, a lot of these have very strict requirements, so I'm not sure how I would do that anyway. Well, right. Lastly, before we get to the control board itself, I replaced these fan grills on the bottom with metal wire ones. I modeled these ones before, and I'm not really much into acoustic design, so when I actually finished setting everything up and assembling everything and turned it on for the first time, I got a very loud, fan noise coming out, which was very annoying, even with lowered fan speeds. So I pretty much replaced them with just metal grill ones. I didn't model them here, but just take my word for it. And so I started off with the same STM32F103 RCT6 chip that I use for the sensor boards. At around $2 a piece, it's cheap enough, has the features I need, and is easier to work with since I've already designed the hardware for it before and wrote some firmware. If I found myself in a state where I needed more features, I could of course switch to the next tier of STM32 chip, but fortunately for me, the one I picked managed to work out just fine. Perhaps I should have splurged actually for the next tier, the one with floating point hardware, as that would have made velocity curve calculations easier to set up, but a bit too late now. Let's move on. So in addition to the main chip and its passives are the various power connections, power LED indicators, and the bulk capacitors. The board seems quite empty like this, so let's get to populating it with features. So starting from the most vital and moving towards the I have extra pins, so why not add some extras we have? The SPI bus connection to communicate with the sensor boards along with the 2 toggle lines for synchronization and direction, plus the 5-volt connectors and the 3.3-volt connectors. That all connects to the chain of 11 sensor boards, each one kind of connected to each other. Next up, we have the USB MIDI controller for sending MIDI data to the main computer, and the 4x20 LCD screen connection, which, along with the connection to the Rotary Encoder / push button, should allow me to modify the various settings and parameters of the device without needing to flash new firmware every single time. If the LCD panel that I'm going to flash somewhere in there looks familiar, it's because I got the idea from the Mendel-style 3D printers like my Prusa MK3. Moving on, the last part of what I consider as the bare necessities are the 4 pedal ADC units, one for the single pedal that I used for testing using my Korg SP250 piano, and one for the triple pedal connector for the GFP3 Kawaii, I believe, triple pedal unit that I bought and plan to use for this piano. So with what is now on the board, the piano would work as I need it, reading note on and off data along with the pedal states and sending it all outwards towards the main computer. The LCD screen and the knob will allow navigation of the settings menu and changing the various parameters. So yeah, everything else is basically just extras I don't plan on using at the moment, but they might become useful later, so why not? In fact, I could have connected this USB connector directly to the main chip itself, but it's actually easier to have a dedicated chip to control the serial to USB conversion for MIDI. Plus, that way, I have options such as, for example, adding a second USB controller with exactly the same firmware. This way, I can use this external MIDI connection to connect some external PC, just in case we want to use a different device than the onboard mini PC. At the same time, I've also added the MIDI I/O connections, as it's something that most digital pianos include. Not really necessary for my use, but at the same time, same way as with the second USB connection, it's just nice to have. As a bonus, it helps out quite nicely during firmware development, as I could use it as a debug MIDI line for testing the USB MIDI bridge, so it served its purpose well, let's say. And finally, we come to the parts of the design which are pretty much completely future-proofing. Essentially, if I decide to add a front panel to the piano with a bunch of buttons and sliders to do things such as change the reverb or switch out the piano presets, I can just connect them directly to the control board without having to redesign and reorder the entire board, or design a very specific board that kind of outputs as MIDI and uses one of these connectors in between to pass the signal through. So there are options, but it's just easier if it's an all-in-one solution. In fact, let me just hide this for a second and switch over to Fusion so you can see what I mean. So the way it is right now, this board this cutout right here is for the, well, LCD screen. Let me hide that so you can see what I mean. So right there is going to be the LCD screen with the rotary encoder so you can adjust the settings. But overall, like, this is a very clean outline. You know, there isn't anything sticking out. At most, you can say, like, you've got the DAC right here with the power buttons and, you know, connections to USB and mini SD card. But most of the controls are through the touchscreen here, and everything else is just a very clean interface. So if I was going to add a front panel, I might do it right here. So maybe like some buttons along the side here and along the front edge here. It would kind of detract from, you know, the overall aesthetic of it, I think. But once again, like, it is an option. I don't plan on doing it right now, but if I do in the future, it's just easier to have this as part of the board itself than having to do the redesign. So let's move on. So talking about these future proofing. So step one, we have the extra rotary connection, pretty much exactly the same as the display rotary, except, you know, as an extra one. So it has a button and you can sense if it's rotating left or right by however many. Not sure what I'd use it for, but it's there. It could be used. It connects. It's easy to work with. Second, we have the 12 button digital inputs for buttons. We have button 1, 2, and 3 right here. All of them with their own circuitry to make connections easier. And lastly, we have the 9 ADC channels for sliders. 9, right? Whoops. Oh, well, actually, that's 6. Oh, well, things changed since I guess I wrote this script. Anyway, this takes care of the surface level of the design, so let's get into a bit more detail in terms of the actual schematics here. Before I continue, let me warn you, the rest of the video covers the control board schematics with less 3D board renders and more electrical diagrams, so if that's not your cup of tea, I completely understand. Feel free to click away or go to the next video if it's already out. If you're looking for suggestions, maybe go listen to the pieces I recorded on this piano. Well, that's all. Back to your regularly scheduled programming. So in terms of the main clock, I decided to switch away from the crystal oscillator that requires capacitance matching as I did with the sensor boards. And instead I simplified things by just going with a single chip crystal oscillator that outputs a digital signal instead. If I was to redesign the sensor boards, I'd do exactly the same thing there as well. So this clock signal is then copied by the main chip out of its master clock output signal here, which goes into USB 1 as its input for the clock signal, is copied again as an output over here, and goes into the second USB chip. As long as the traces are wired properly, it should, and it does, work fine. I mean, 8 megahertz is not exactly too high speed that I can't just use a 50 ohm impedance coplanar trace on a 2-layer board and expect it to work without multiple iterations, so should be all good. I kind of get a 3-for-1 deal here as well since I'm just using the single clock crystal for the 3 chips. Moving on, the LCD connection uses an I2C communication line, which requires 5 volts, which isn't actually as much of a problem as I feared for the 3.3 volt STM32 chip, because most of the STM32 chips, including the I2C pins, are 5 volt tolerant. I just had to make sure that the 5 volt line isn't powered on before the 3.3 volt line, which I did by adding this LCD power switch that could be toggled by data signal from the STM32 chip. This also means that I can turn off the LCD when it's not in use, so, you know, win-win. Let's count off the various communication lines real quick. So we've got the I2C line for the LCD screen. We have the SPI line for the sensor boards. We have the MIDI in and out for the serial via UART line, and 2 more UART lines for the USB MIDIs 1 and 2. So that's a total of 5 communication lines that all need direct memory access, or DMA, for both directions. Well, the LCD needs it in one direction, but who's counting? In either an amazing stroke of luck or good planning on behalf of me personally and the STM32 developers, none of the DMA channels clashed after I switched out and decided on which SPI line to use. So that actually means that I could go on ahead and make use of this chip without having to search for a different one. So it was rather nice. And lastly, for this page, we have the power connections. When I was laying out the sensor boards, I needed a 5-volt line for the LEDs, as well as a 3.3-volt line for the controllers, and everything else. So since it was my first time designing a board, and I didn't want to reorder them if they didn't work, I decided to forego any sort of power regulation and instead provide the 2 voltages as separate lines to just be connected to their own dedicated power supplies. Now that I know a bit more about electronics, I realized this wasn't exactly the best of solutions, further compounded by me not adding any decent size bulk capacitors on either power line on every sensor board. So now that I'm working on the control board with all the inherited problems, I decided to add a set of large bulk capacitors to cover both the control board and the connected sensor boards to the tune of a large polymer bulk capacitor on each power line, a medium size polymer bulk capacitor specifically for the control board, and the typical small sized ceramic bulk capacitor. And naturally, all the chips have their own decoupling capacitors, but that's more along the lines of as per reference. Is this a good setup? I certainly hope so. Testing with all the boards fully assembled gives me 5 volts and 3.3 volts respectively on the inputs, and 4.9 volts and 3.2 volts at the very last of the sensor boards. Pressing down all the keys at the same time to turn on all the LEDs on the 5-volt line brings its furthest point down to 4.8, which seems to be well within acceptable limits. So far, everything seems to work, and I've left the piano running for 2 weeks nonstop without problems, so without expensive tools to conduct in-depth testing, I'm just gonna have to give this a pass. Communications wise, I can run 4.5 megabits per second over the SPI lines, though the 9 megabits per second maximum that the STM32 chips can support do cause issues. Not sure if it's the signal integrity problems or firmware issues. In any case, even with 4.5 megabits per second, I can get a full readout of the 88 keys in around half a millisecond, which I consider to be good enough. Keep in mind that this half a millisecond is part of latency only and has no impact on the precision of the note velocity sensing, since that is done individually by each sensor board with a dedicated timer for each of the key running at 8 megahertz itself, which gives me more than enough granularity for even like 14-bit resolution note on events, let alone the regular 7-bit MIDI resolution. Moving on, I decided to have the main chip handle the MIDI signals in serial format on all 3 lines, with 2 of them being converted to USB with a dedicated STM32 chip, such as this one right here. Now, serial to USB for MIDI is apparently riddled with exceptions, so using a standard UART to USB chip wasn't the best of options, not to mention that the good ones cost like 4 times as much as the STM32 chip, and most can only be flashed once, so if I got something wrong when setting them up, I would have to either toss the board or desolder the chip and replace it. So yeah, in the end, just using exactly the same STM32 chip that I've been using thus far for the USB bridge made the most sense. As a bonus, the firmware I developed for it could be used for, standalone serial to USB MIDI bridges, so it might be helpful to others looking for it like I was when I got started. The design is rather simple. There's the UART and USB lines as the two ends of the bridge, the 3 status LEDs for USB connection, and the 2 for the signal directions, the clock line in and out, the SW debugging connection, the USB voltage sensing circuit that's used to tell the chip that there's someone on the other side of the USB wire, and the 1.5K resistor for the USB's positive data line pull-up, which is used by the chip to signal whoever is on the other side of the USB that there is someone on this side ready to connect via USB 2.0 full-speed protocol. It's a bit more complicated than in the reference schematics, mainly due to me powering the chip via its own power instead of through the USB wire. So it's possible for the chip to be powered, but the USB to be disconnected, or for the USB to be disconnected and reconnected without losing power to the chip. In terms of the USB protocol itself, fortunately for me, STM32 has a decent USB peripheral driver already written, so I just had to change a few things, rename it and so on, to have the device be recognized as a proper MIDI device, as well as giving it the name Janko Piano instead of having to make my own driver. So yeah, a weekend of figuring things out, and I got the firmware all squared away with DMA connections and buffers on both lines to prevent any dropped packets. Quick echo test later confirms that it works as intended, and that was the last I used the main chip's serial MIDI outputs for anything. It's been USB all the way from then on. Now, speaking of the serial MIDI, let's briefly cover it. So, serial MIDI is something that is well documented online and something I've already figured out previously when I was working with the development board for the 8-key prototype. It technically has a 3.3 version or 3.3 volt version, but I felt it best to go with the classical 5 volt design and simply put a 3.3 volts to 5 volt signal repeater on the MIDI outline. For the MIDI inputs, there was a bit too much information online, especially due to the arguments for and against the classical components versus the newer ones with respect to the optocouplers. So just to be safe, I went with 2 separate input circuits based around the 2 commonly recommended optocouplers, which I could choose between via a set of jumpers and call it a day. In testing, they both worked perfectly fine, so if I was to make a revision of this board, I'd just go with the logic level output version right here. I tried to wire up the activity LEDs to be connected directly to the MIDI signal lines, but in the end I had a few extra I/O pins on the main control chip, so it was just a lot easier to connect them to it and control them in firmware, just like I did with the serial USB bridge activity LEDs. For the rotary encoders, one of which is going to be used to navigate the settings menu that the LCD display will show, while the second one will be left as an extra just-in-case connection, I treated them exactly the same as with button inputs, so I'll talk about the actual circuit later. The encoders themselves have 3 signal lines, with signal A and B used for calculating the rotations, and the switch signal being essentially just a button that toggles when you click it in on the wheel. Here's an image right there. Unfortunately for me, the STM32 chips have an inbuilt rotary encoder interface through their timer modules, so I just had to make sure that I connected these signals to the correct pins on the chip, and the chip itself will take care of converting the signals into an easy-to-read numerical value without my help. Right, let's talk about the digital inputs for the buttons. As you can see, the circuit diagram here is pretty much identical to the one for the rotary encoders, and though it looks complicated, it pretty much is just a bunch of identical hardware debouncing circuits. See, when a mechanical switch is toggled, it doesn't have a smooth transition, and instead it bounces around for around a millisecond or so before stabilizing. This can wreak havoc upon, the firmware, depending on how the signal is used, so typically this means that you want to solve this issue in either hardware or software, or ignore it altogether, once again, depending on how the signal is used. In my case, I decided to have the hardware debouncing to prevent issues on the rotary encoders. And since I'm already using the parts there, then it doesn't really cost me all that much to put them in for buttons as well. So we have a 10K pull-up resistor to set the button open state to high, which kind of means that when you press the button, it gets pulled low. An RC filter, low pass as the first step of debouncing, and a diode to kind of make the rising and falling edges symmetrical. Finally, there is an inverting Schmidt repeater to add further hardware debouncing. Initially, I put it in purely because I had space on the board, and I was planning on using economic assembly with JLC PCB, which lists them as basic parts, making them practically be free, or just the cost of the parts themselves, instead of including extra charges for a unique component. So I thought, what, why not include them? And when I decided to switch over to regular assembly instead, the added cost was just like $1.50, so I didn't bother removing them. Wired up like this, and with the inverting repeaters, I end up with a high signal when the button is pressed and low otherwise, which is rather nice for firmware design as well. And at last, we get to the analog inputs, the pedals over here and the sliders here. Both are essentially the same, just with a bit of a unique connection for this single pedal unit to allow both mono and stereo style plugs to be used without worrying about shorting out the ground to power. So, still a bit unsure about the 100K resistor over here. Might be a bit too weak or too strong, depending on how you count it. For the single pedal, but if it really does become an issue, I can always put another resistor between the signal and the power line off board, so I'm not going to worry about it. Anyway, all the analog lines are essentially the same. You've got the 100K pull-up resistor to keep a consistent 3.3 volt signal in case that nothing is connected. The same RC low-pass filter as with the button input lines. And in the case of the Kawai's GFP3 pedal unit, the 3.3 volt signal means the pedal is released, while a 0 volt signal means the pedal is fully pressed. So this works out perfectly. And naturally, this isn't true for all pedal units, but that's all something that can be taken care of in firmware with either an auto recognition setting that sets up the value it sees on startup as the released value, or a setting in the menu that could be changed. Back to the electronics, we basically covered everything. Oh, and I haven't been mentioning these, but most off-board signal connections are wired through ESD protection chips, just like this one. You can see them here, as well as in the serial MIDI lines and the USB lines right here. And so yeah, that's it for the control board schematic. As for the PCB layout, I have much less to talk about. I went with the same two-layer board design as with the sensor boards, seeing as how I don't exactly have all that many high-speed lines, and those that I do, I designed with coplanar ground lines to both sides with sufficient vias to hopefully act as fencing and guides, as you can kind of see very much around here. I kept most of the back as a single solid ground plane with minimal cuts along it, just around the range of the main chip, essentially. This isn't to say that the board is perfect, far from it. In fact, I have an ever-growing list of things I want to change or modify, such as, editing the power lines to have a single 5-volt line as input with dedicated linear voltage regulators for 3.3 volts on every sensor board, adjusting the series termination resistor values, double-checking the RC filters, changing out the USB connection sockets from A to maybe B or one of the mini ones. But none of that will make it into my, digital piano. At best, they might be added as version 2 of the boards that, once I publish the designs to open source, with a caveat that I haven't tested the version 2 boards. So, yeah, this turned out to be one of the longer videos in this series, so I don't expect many of you to have actually made it this far, but For those of you that did, thank you very much. Hopefully you found this interesting, maybe entertaining, and I'll see you guys in the next video. You know, as per usual, like, comment, subscribe, all the rest of the jazz. Later.